Now let's see about the internal resistance of a cell. Now what is meant by resistance? We know that resistance is nothing but it is the opposition to the flow of charged particle. In the case of our consideration of this electricity, we generally take as this charge as electron. So opposition to the flow of free electrons in the conductor, we simply call it as what? Resistance, right? And this resistance, now this is concerning about a cell. You know that inside a cell chemicals are placed inside a cell, and that inside the cell chemical reactions are taking place, reduction and oxidation are taking place. We call it them as redox reactions. Got it? So due to those chemicals, okay, those, if it is connected with this circuit like this, suppose your cell here and external resistance here through this connecting wire, if you make a circuit, then what happen? The current will be flowing here like this, conventional current I mean, but electron will start flowing from this negative electrode through the external circuit and it comes to this positive terminal, right? And what happened? This external circuit is completed, current is flowing opposite to the motion of those free electrons starting from the negative terminal of the cell through the external circuit, and it comes to the positive terminal. This is outside the circuit, so we call it as external circuit. But inside the cell itself, the ions are moving from the positive plate to the negative plate inside the cell itself. So those opposition, the opposition, okay, offered by the electrolyte, the chemical present inside the cell, the opposition offered by the electrolyte when ion moves from the positive plate to the negative plate inside the cell itself, we call it that opposition to the flow of ions inside the cell itself from one electrode to the another electrode. We call it that as what? Internal resistance of a cell. So it is inside the cell, so we call it as internal. Why we call resistance? Ions are moving from one plate or one electrode to the another electrode. So inside that cell itself, when ion moves from one electrode to the another electrode, they what? Face some opposition. That opposition to the flow of this ion from one electrode to the another electrode inside the cell itself, we call it that as what? Internal resistance of a cell. So there are various factors, okay, there are various factors which affect this internal resistance of a cell. It depends upon the nature of the chemicals, or rather the electrolyte that is placed, okay, so as to make that as a source of EMF. It also depends upon what? Depends upon the nature of the electrolyte. As I said, it also depends upon the distance between the two electrodes in the cell itself. If the electrode is very close to one another, then what happen? Less length need to be moved by the ion from one point to another point, right? If these two electrodes, if they are very close, then what happen? The opposition will be less. What happen? Internal resistance will be less. If these two electrode, positive electrode and a negative electrode, if they are very far away, then what happen? The ions need to move for a longer distance. So in that case, what happen? More opposition to the flow of this ion. So what happen? Your internal resistance will be high. Got it? And if your electrolyte, okay, if it is of the nature that it can flow these ions very easily, then internal resistance will be less. Got it? And it also depends upon the common area between these two electrodes. Okay, if you are having two say suppose plates, okay, you must be remembering in the case of Nickel cell or Daniel cell, if you are having that electrode as just like a thin plate, okay, then what happen? The common area of the two electrodes, okay, either it may be what? Zinc or copper. In the case of what Nickel cell, this what your positive plate will be a carbon one, and this negative plate will be a zinc plate or zinc rod. So the common area between these two electrodes, okay, smaller of these two electrodes, suppose if your zinc is smaller than that of your carbon, then the smaller one, the area of the smaller electrode will be the common area. Okay, so larger the size of the electrode, lesser will be the internal resistance. Why? Because more and more ions may be allowed to flow from those electrode to the another electrode. Got it? So what happen, larger the area, that means common area, less will be the what, internal resistance. So your internal resistance is inversely proportional to the common area. Smaller the common area, then what happen, larger will be the internal resistance. Got it? And it also depends upon, lastly, it also depends upon the nature of these electrodes. Okay, whether these electrode can easily gives out or emits out that ions readily from those surface of these electrodes, or whether they are not readily emits those ions or electrons from those electrodes. So it depends upon the nature of the electrode also. So all these different factors affect what the internal resistance of a cell. It is also given here. You can pause this video and you can note down. Okay, it may be asked in the practical exams also. Practically you need to know it. So let's try to find out the relation between the internal resistance and that of this EMF and potential difference. The relation between what internal resistance and what internal resistance with that of EMF and the potential difference of a cell. Now you can do from here like this. As I told you that EMF is the maximum potential difference, and the maximum potential difference will be equal to the potential difference across the ends, okay, of the two electrodes when the current is passing or drawn from the cell, plus the potential difference developed, okay, inside the cell itself. Suppose we can't draw that internal resistance inside the cell itself, rather we take it outside. Okay, if you want to draw, then we can draw like this also. Suppose if you are having two electrode, for example, like this, two electrode of a cell, okay, you take it that this is the two terminals of the cell. So you take it these as positive. Let me take it little bit longer like this, okay, just to represent the cell, and this side is negative. So what happen inside outside the external, outside the cell itself, I mean in the external circuit, you will have these resistors, no doubt. Got it? Capital R. Got it? So inside the cell itself, you can have that internal resistance here, and that internal resistance we denoted by small r. Okay, so there is a resistance in between the two electrodes of the cell, okay, inside the cell, I mean. So what happened, the potential difference across these two electrode, okay, will be equal to what, this potential difference and the potential that is developed across this when there is no current passing through it. Suppose when there is no current passing through it, means the key will be off somewhere here. Okay, when it is off, the potential difference developed there, we call it as E, right? Now when the current is flowing like this, the potential difference across this R will be the potential difference across the two electrodes of a cell, right? When the current is flowing, what happened, the potential difference here at the two electrode will be also equal to the potential difference here or drop here. Got it? Across the resistor. So what happened, your current, okay, will be flowing in this way. So the potential difference across this R, okay, and the potential difference across this internal resistance, the sum of these two potential difference across the cell or across this resistor, we will call it that as simply V, and the potential difference across this internal resistance R, that will be denoted by small v. Okay, so your maximum EMF or the maximum potential difference we call it that as EMF. This EMF will be equal to the sum of the potential difference, okay, of a cell plus the potential difference, okay, across that internal resistance. Got it? So if you make it that V is equal to IR, suppose if the current flowing here is capital I, then what happen? The potential difference across these two resistors, the two terminals of the resistor, will be equal to the potential difference of the cell. So we can write V is equal to IR from Ohm's law, and the same current I will be flowing here across this internal resistance also. So we will make it that what V small v as I into small r, where I is the current that is flowing through this circuit, okay, like this. Whatever the current that is flowing outside, that much current will be also flowing inside the cell within the electrolyte, okay. So if you take it that I common, then you will get like this. So the relation between what your current, internal resistance and EMF or the external resistor, that will be given by this relation. And if you want to relate this internal resistance in terms of what your EMF and potential difference, then it will be like this. Think that your EMF is denoted by V, potential difference by V, then we know that EMF is greater than the potential difference of a cell. If you want to know how much it is more, then you have to take a difference, right? Okay, so E minus V is a difference in the potential difference. That much potential difference across the internal resistance, okay. Symbolically, we generally draw like this, okay. Cell, internal resistance drawn outside. Got it? So the EMF, the potential difference, or the maximum EMF, we call it as simply EMF. So EMF is more than the potential difference of a cell. So by how much it is more, the potential difference or the potential drop across this internal resistance, okay. So the difference will be equal to what? IR, the potential drop across the internal resistance. So if you divide it, this E minus V by R, by I mean by I, that means I means what? V by R, okay. V is equal to IR, so your I will be what? V by R, right? So if you divide it, then you will get just like this. So your R will be equal to what? E by V minus 1 whole into what? R. This relation is very important and you need to remember this, because what happened in the case of this potentiometer, okay, we will learn later on that potentiometer. So this internal resistance can be measured by what? By using your potentiometer, not by voltmeter, okay. Voltmeter will not give you the correct reading of that internal resistance, or rather EMF, but your potentiometer will give you the actual measurement of either your EMF of a cell or internal resistance of a cell. That can be done by using what? Potentiometer. So while doing that potentiometer, this formula need to be remembered at that time, okay. So E by V minus 1 whole into what? R. Got it? So this is the what? Circuit equation. Got it? You can call it. Yes. Now let's see about the internal resistance in a different form. That means your internal resistance and the external resistance with that of your EMF and potential difference of a cell, it will be related like this. This is very easy. You just go through it, pause the video and you just go through it, okay. This is very easy, no need of much explanation, okay. But I'm going to tell you about that EMF and potential difference with this diagram, okay, that I have already told you. Now this is the what? Resistance box. That means resistance box is for what? Just to prevent a large current flowing through the circuit, okay. Instead of going the large unknown current, we usually place a resistance box, high resistance, in the circuit, so as not allow to pass a non-high current, okay, just to prevent it. So you can take it this as capital R, the external resistance in the circuit, right? This is a cell, okay. The potential difference across the two electrodes, okay, that will be measured. When no current is drawn means when the key is what? Open. That means your circuit is open circuited. Okay, so when no current is drawn from the cell itself, the potential difference across the two ends of these electrodes, that will be measured or called as EMF of a cell. But I'm telling you that your potential difference measured by using voltmeter will not give you the correct reading. Okay, instead we can use it for measuring EMF. We can measure what? The potentiometer. Why? Because potentiometer will give you the accurate reading than that of the voltmeter. Why? Because voltmeter draws some current, because it has its own what? Resistance. It has its own coil there. Okay, so some current will surely be drawn from this cell itself, but in the case of potentiometer, no such current will be drawn from the cell. Okay, now in the case of potential difference of a cell, what happen? This key will be closed. Okay, key will be closed and the circuit will be there in the external circuit. So some current is drawn from this cell itself, okay, through the external circuit. So during that time, what happened? The potential difference across the two electrode of a cell, we call it simply as potential difference of a cell. Got it? Yes. Now let's go to the last part, that is nothing but the series combination and parallel combination of a cell. It is very easy for this. Don't make it don't think it that it is difficult. Okay, think that it is very easy and it will be easy there. Okay, now as I told you that in the case of combination of resistors, two electrodes, two connecting leads are there for each and every of these cells. You may be taking that as positive electrode, negative electrode, so it will have two connecting leads. Okay, so if these different two or more cells if connected one after the another, okay, then we will call it that combination of cells as series combination. Now from positive terminal, negative terminal, alternately you have to connect it. Okay, this is the negative terminal of one cell, you need to connect to the positive terminal of another cell. The negative of this cell will need to connect to the positive terminal of the another cell alternately, negative, positive, negative, positive, negative, positive, so on, like that. So if they are connected in this way, then we call it those two or more cells are said to be connected in series. Now as I told you the peculiar properties, when the current is flowing in such type of combination or connection, what we call as series connection, then what happens? Same current will be flowing across these different cells. Okay, your EMF of the battery, right? The EMF of battery is the sum of the individual EMFs. Okay, whatever the potential difference across these two ends will be equal to the sum of the EMFs here, E, E, E. Suppose if these are taken as of the same or similar cells of whose EMFs are E, 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 internal resistance also same, R, small r, like that, then this EMF will be equal to, the total EMF I mean, will be equal to E1 plus E2 plus E3. Here we are taking up what? Similar cells, so your E will be all same. So we need to find out what is this total current. We need to try to express this total current in terms of this E and R. Okay, and we need to see whether the current is dependent on the number of cells. Now let's take it that such similar cells are connected in series. How many cells? N cells. So such N cells are connected in series. Let's take it, of whose EMF of individual cells is denoted by E and internal resistance by small r. Okay, and it is connected to the external circuit, say R, right? So the total EMF of these different cells connected in series, now we will call it as battery. So the total EMF of this battery will be what? It will be equal to NE, where N is the number of cells connected in series. Okay, and we have taken that these cells are similar, or you can say, or you can call them as identical cells also. Okay, so your total EMF will be NE. If you are having only two cells, then it will be 2E. If you are having 3 cells of whose EMF are E, then it will be 3E or thrice E, you can call it. So let's take it that there are n cells connected in series. So what happened? Total EMF will be equal to what? NE, right? And the total internal resistance of all these cells connected in series. Now we know that equivalent resistance for connection in series, okay, connection of those resistors, then the equivalent resistance will be equal to the sum of the individual resistors. Okay, if you are having n cells, then there will be n small r's connected in series, right? So its equivalent resistance will be what? R plus R plus R, so on up to n times, okay, for n cells. So you will get as NR will be the total internal resistance. Now total resistance will be what? Total resistance in the circuit, as these cells and the external resistor are connected in series, current will have to flow like that through this, okay, resistor, and then it will go to different individual cells. So they are connected in series, same current is flowing across this external resistor, internal resistances, right? So what happened? Total equivalent resistance will be what? NR plus capital R. This will be the total resistance of the circuit. Total what? Potential difference of what? The cells connected in series. So what happened? Your current will be equal to total EMF, or rather total potential difference, to the total resistance. When we try to find out I will be equal to what? V by R by Ohm's law. V means what? Potential difference, okay, or rather you can call it here as what? Potential difference, no doubt, because current is drawn from here like this. So your total potential difference, that will be equal to your total EMF, right? That potential difference across these two n will be also the potential difference here. Got it? So what happened? Your current I will be equal to what? NE. This is the total potential difference divided by the total potential difference divided by the total resistor, okay, total resistance you can call it. So this is the relation for the current flowing through this circuit. So we need to see this current, whether this current depends upon the number of cells. We need to see if it depends upon the number of cells, and then that condition will be profitable. Now I'm going to tell you that condition, okay. Suppose, let's take a situation that this external resistance is very much less than the sum of the internal resistances of those cells, okay. That means if your R is very much less than the total internal resistance of the cell NR, then what happened? This R is so small in comparing to this NR, so this R can be neglected, and the relation will be equal to what? I is equal to NE divided by NR, right? So when you cancel this N from the two, then what happened? You will simply have what? Get as E by simply small r. That means your total current will be equal to E by R. Got it? But this expression is independent of the number of cells in. Got it? There is no n, small n here. So it will be equivalent to the amount of current flowing or given by a single cell. Got it? By a single cell. So it is independent of the number of those cells connected in series. If you are having thousands of cells, such identical cells connected, then what happen? If this is the condition, that means external resistance is very small when you compare with that of the internal resistance, then it will be just equivalent to the current, okay, given by a single cell. So it is of no use whether you are connected 1000 cells or whether you are connecting 1 cells, okay. So that one, what happened, if this is the condition, that means when the external resistance is very much less than the total internal resistance, then this type of connection, that means series connection of resistance, is not profitable. It's of no use, I mean. But the other condition, when this internal resistance, the total internal resistance, is very much greater than this what external resistance. That means when NR is very much less than that of the external resistance R, okay, when you compare these two, if this one is greater, if external resistance is very large when you compare with this NR, that means this is very small, R is very large, the sum of these two will be nearly equal to what? The larger value R, capital R. So what happened in this case, it will be equal to what? N times of E by R. So E by R is nothing but this is what? The current that is produced, okay, by the total what? Cells connected in series will be equal to what? N times of E by R. So this is the maximum current that can be produced by those cells connected in series. And now a factor N is there. If you are having 2 cells, then this will be 2 times. If you are having 3 cells, then this will be 3 times. If you are having 1000 cells, then this N will be 1000. So it depends upon, it means this current depends upon the number of cells connected in series. So this connection of series is profitable, useful when the external resistance is very much greater than the total internal resistance of a cell. Got it? It depends upon this N. Got it? So series combination, you need to note down this point, that series combination or connection of cell is useful or is applicable only when the external resistance is very much greater than or larger in value than that of the total internal resistance. Got it? This will be opposite, just opposite in the case of parallel connection. Let's see the last topic of today's class. Okay, cells in parallel connections. When these positive terminals of those cells are connected to one point, negative terminals of these cells connected at one point, then we call it such type of combinations as what? Parallel combination. Now, as I told you, the peculiar properties in the case of series and parallel connection of resistors, okay, those peculiar property will also be there in this parallel connection of cells also. Okay, same potential difference will be there across these different what? Battery or different cells, I should say. So as these are of identical cells, what happen? The potential difference across these different individual cells will be what? It will be having the same EMF, E. Okay, the potential difference here for this, it is E, no doubt, here also E. So this E will be the total potential difference, okay, or EMF you can call it, and being connected in parallel. Okay, the internal resistance, the what? Total internal resistance, you can take it like this. Let's take it that 1 by R P connected in parallel. Okay, R for equivalent resistance, P for connected in parallel. Let's take it that these are the individual resistors, they are connected in parallel, so it will be equal to what? 1 by R. Okay, 1 by R. If you take it this as a first resistance, then for the second resistance also you have to take it as 1 by R like this. Got it? For the third resistance also you have to take it 1 by R, and such 1 by R you need to go on, okay, as long as how many number of cells you are connected. Got it? You have connected. So suppose here in our today's class we have taken that such n cells are connected in parallel, so we need to go n cells. Okay, first, second, third, then you need to go up to n times. So if you are having only 2, then it will be 1 by R plus 1 by R, that means it will be 2 by R, right? If you are having 3 cells, then it will be 1 by R 3 times, so it will be 3 by R, right? So your equivalent resistance RP, if you take it this reciprocal out again, then it will be equal to RP. So if you are having only say R n cells, then it will be equal to, this will be equal to what? N by R. 1 by R, 1 by R. When you keep on adding to n terms for n cells, then it will be what? R by n by R, right? N by R. So if you take the reciprocal, then it will be equal to what? R by n. Got it? That is what I want to explain you. So your equivalent resistance of those internal resistance connected in parallel will be equal to what? R by n. This R by n, okay, it will be replaced by a single resistor which is equal to Rp. So that Rp and this external resistance R, they are connected in series again. So your total equivalent resistance will be what? This Rp plus capital R. You can call it this as R by n plus R. Now we need to find the current, and we need to see whether that current is depending upon what? Your number of cells or not. If it doesn't depend on the number of cells, then it will not be profitable or useful. If it depends on n, then it will be profitable. Let's see. Your current I will be equal to total EMF divided by total resistance in the circuit, right? Now in this case, what happened? If this R by n, here it was R by n, okay, after doing that simplification, it goes here like this, okay, R plus R by n. If you take it the LCM, then it will be what? It will be R plus NR divided by n. Got it? That n goes here. Clear? Should I show you that one also? Okay, let me show you. Now this, what I will be equal to what? The total EMF is what? Total EMF is E, right? Total EMF is E, and total internal resistance is what? R by N plus R, right? So if you do the LCM for the denominator, then it will be E, right? Then LCM will be N, and this will be R, small r, plus NR, right? Got it? So your N can be brought in the numerator, then it will be NE, what is having here, NE, okay, plus R plus NR, or you can write NR plus small r, okay. That is what I have written here in a very short way, so you can see that one. Let me remove this whatever I have written so that you can see it very clearly. Yes, like that. Now see, so what happened when these NR and R, we are going to compare these two, or rather R by N with the capital R. Got it? So if when you compare these two, if these R by N is very much greater than this R, okay, when R by N this is very much greater than R, then it is profitable. Got it? N by R. This is just the opposite. When the external resistance was very much large, it compared to the internal resistance, in the case of series combination, it was profitable, right? But in this case, let's see, instead of saying in that way, we can also say that if R is very much less than R by N, got it? Or rather, if you take it R very much greater than R by N, you will have it like this. Got it? If external resistance is very much large than that of R by N, that means total internal resistance, then it is of no use. Why? Because there is no factor N here in this, in the expression or in the equation of current. But when R external resistance is very, very small when you compare with that of a total internal resistance R by N, got it? External resistance is very small in comparing to that of a total internal resistance, then I can be expressed as N times of E by R, E by small r. That means this will be very, very small when you compare with this R, okay? That is the meaning for this one. Got it? If external resistance is very small in comparing to the R by small n, that means your NR is very small, So what happened? It will be equal to what? NE divided by R. Got it? So as the factor n is there, so it is profitable. If you are having 2 cells, then it will be twice. If you are having n cells, then it will be n times. So what happened? Your parallel combination of cell is useful or profitable only when your external resistance is very small in compare with that of a total internal resistance. Got it? With this we will come to the end. We come to the end of our today's class. Okay, thank you.